In this work, a holographic flat length antenna capable of simultaneously transmitting two independent propagating orbital angular momentum OAM beams operating at 60 GHz is demonstrated. The design involves the processes of recording and reconstruction.
This figure shows the configuration of our OAM multiplexing antenna. The antenna was designed such that when free source 1 is excited, the lens can generate an L1 armor beam propagating along the both side direction. Likewise, as free 2 is excited, an L2 armor beam can be launched. In this manner, two coaxially propagating OAM modes can be generated simultaneously to provide two separate armor channels. The holographic theory is developed to obtain the design composition phase distribution of the flat length. The synthesized result is shown in this figure. We derive the condition to suppress the residue term. And this figure shows the design phase distributions and their corresponding Fourier radiation patterns in UV space. The value of H of H is selected as 1.6 here to completely suppress the residue term. A wideband CSAT transmitter element is used as the building block of the flat length. The open angle of the middle CSAT modality layer is tuned to realize the required phase distribution. We use the broadband ME dipole antenna as the free source of the flat length. The antenna radiation performance was measured by the far-field and near-field robotic radiation measurement system, which is developed by the Stackey Laboratory of terahertz and millimeter waves. These two figures show the schematic and measure far-field radiation patterns when free 1 and free 2 are excited respectively, and these two figures show the schematic and measure near-field phase distributions at different frequencies when free 1 and free 2 are excited respectively. It can be observed that the -1 and +1 armor modes can be successfully generated. As a result, two independent wireless channels can be provided by this OAM multiplexing lens antenna. This work was conducted at the Stackey Laboratory of Terahertz and Millimeter Wave, City University of Hong Kong. For more details, please refer to our paper. Thank you for your watching.
Hello everyone, this is Javier Melendro from Polytechnic University of Madrid, and I'm going to show you here in this quick presentation our most recent paper that consisted in the design of a gradient index lens with an integrated polarizer for dual circular polarization at W1. So, as you may know, a gradient index lens has a relative permittivity that decays from its center to its edges. This is due so the lens can compensate for the different paths of the rays in order to achieve plane wave emission. We would have the relative permittivity profile shown in the blue curve. However, in order to approach it to a practical solution, we need to approach this blue curve to a step function. This means that we designed a 5-layer lens with given relative permittivities. Now, to achieve the exact relative permittivity required for each layer, what we did in the paper was to perforate each layer as shown in the image. So here are some results of the gradient index lens antenna. As you can see, the lens can collimate the rays into a single direction, achieving plane wave emission. Here are some cuts of the radiation pattern. As you can see, there's been an enhancement of the directivity, a notable enhancement of the directivity. Besides, if the square waveguide is displaced along the focal plane of the lens, the lens can achieve beam reconfigurability up to ±30 degrees in the azimuth and elevation planes. Now, comprising the dielectric polarizer, here we can see how when the T10 mode is excited in the square waveguide, the vertical polarization is converted by the polarizer into right-handed circular polarization, Whereas if the T01 mode is excited in the square waveguide, the horizontal polarization can be converted into left-handed circular polarization by the polarizer. The whole concept of the polarizer is based on an anisotropy in the dielectric slabs and the definition of two effective permittivities. Now, showing some results of the beam reconfigurability, as it can be seen, as the square waveguide is displaced along the focal plane of the lens, the beam can be tilted up to 30 degrees, keeping a low axial ratio below 3 dBs. Now here's a picture of the gradient index lens with the integrated polarizer that was manufactured as a single piece. A dielectric frame was also manufactured to achieve beam reconfigurability by displacing the CP lens with respect to the feeder. Now, to end, I'm going to show you here the validation by measurement of the CP lens. As you can see, the main beam can be tilted up to 30 degrees. Thank you very much.
In this video, I would like to present our paper entitled 2D Wide-Angle Multi-Beam Flat Grain Lens with a High Aperture Efficiency. Well, to serve long-distance communications for 5G and beyond wireless systems, antennas are designed to have high gains to compensate for high path losses. While on the other hand, multi-beam radiations are highly demanded in order to support connections with multiple distributed users. Well, among different antenna types, lens antennas can be designed for multi-beam radiations with wide operating bandwidth and high gain. Well, particularly flat gradient index lens, which has varied refractive indices on a flat geometry, is very attractive due to its advantages of low-cost fabrication and easy implementation on practical platforms. However, for state-of-the-art multi-beam flat grain lenses, it's still challenging to achieve both high aperture efficiencies and wide beam coverages in a 2D scanning range. So to address this problem, we have presented a new methodology for multi-beam grain lens. So first of all, let's look at the traditional design method. Basically, the lens profile will be analyzed from a central feed point in order to produce ball-side radiation. Then by simply shifting the feed point linearly along the focal plane, oblique radiation beams can be achieved. However, this method can only support small beam coverage. So in order to extend the beam range, in the newly developed method, we analyze the lens profile from an offside feed point. Then simultaneously, we will analyze the lens from its symmetrical feeding scenario. Then after that, the feed point at the center will be calculated to enable optimal ball-side radiation beam. Finally, with the three determined feed points, a focal arc can be obtained for multi-beam radiations. Then we extended this analysis method to a 2D lens aperture, which has gradient refractive indices along both radial and azimuthal coordinates. Then in the final implemented model, microstrip petro array antenna has been utilized as the feed source in order to save space. Then we can see by using the new analysis method, a wide beam coverage has been achieved with low scanning losses for multi-beam flat grain lens. Besides, a high aperture efficiency of up to 66% has been obtained. Also, to the author's best knowledge, this is the first time that a 2D multi-beam flat grain lens has been implemented. Thank you for your attention.